So good morning, everyone. So I'm presenting a paper called Why Should I Trust You? Explaining the predictions of any classifier. So we just heard about the normalizer-free ResNet. Even though you can train all these different kinds of models, right? There are two issues that can affect you during your model training. So the first one is something like it's called data leakage, which is something like an unintentional leakage of some signal from the training data into the training data, so that when you train it, the model actually picks up on these unintended signals in the data rather than what you actually want it to learn. And for the second one, it's called data set shift. So that happens when you have a set of training data and then your training data doesn't correspond. It's a different population from the testing data. So you train it on some specific data set, and then when you try to test it on some real world data, you find that the predictions are off. But these things can be very hard to identify without any tools. So what this model does is that it allows you to actually detect this kind of issues. So the first example for data leakage. So you can see that we are trying to classify, is it a wolf or is it a dog? And for all the wolf pictures, they all have light backgrounds. And for the husky pictures, they have a dark backgrounds. But if you just check on the accuracy, you can't really tell what the model is trying to predict. But if you apply some interpretable explanation to the model, then you can actually see what the model is looking at. What parts of the images are actually affecting the prediction. So you can see that when you're predicting a husky, it's not actually looking at the dog, it's looking more towards the background. And when the bottom left, you see when trying to predict a wolf, it's actually looking at the snow around the dog rather than the dog itself, or the wolf itself, or husky itself. Yeah. Okay. For the dataset shift, this is an example from the 20 news corpus. So there are two algorithms here, on the left, on the right, and it's trying to classify, is the document from the subject atheism or is it from Christianity? And the magenta bars actually show like how much each word affect the prediction of atheism. And you can see that for algorithm 2 on the right, the words that are actually important are things like porting, host, and re, which is like regarding some subject header. So these are not the words that actually that should not be influencing the class, but the model actually takes these words and says that, oh, these are the words that always appear in atheism. Therefore, the message is from atheism. The desired characteristics of this interpretable model classifier. So first thing, it needs to be interpretable, right? You need to be able to understand how the model is classifying something. Next thing is the authors want it to be to have local fidelity, which means that it needs to be able to explain the examples in that area, in that region. So similar examples should all fall within this explanation. It doesn't need to be a global level fidelity. So it means that if I take two very different examples, the example that apply to the explanation for first example might not apply to the second example. And lastly, it's model agnostic. So you can actually throw in any different kind of model you want into this explanation model, and it actually allows you to compare like how does each model make its predictions. Okay. So we go to the intuition, which is line. It's local interpretable model agnostic explanations. And essentially what you have here is they are trying to show some complex decision function. So you're either purple or blue, or not purple, pink or blue. And then what you are trying to do is trying to explain the big red X. Why is it classified as the red? And what line does is that it actually takes examples from around the surrounding regions. And so you see like the thinner red crosses and the larger blue dots. So the size of those shapes actually represent how much it's weighted inside line. So you weigh closer examples more than the further examples. So you still take examples from far away, like if you look at the bottom right, there's still like few dots and crosses there. But you actually weigh the closer examples more highly when you try to explain the big red cross. And with this example, so what you can do is you can actually create a linear decision function, the dotted line, and that helps you to explain why the big red cross is classified as a red cross instead of blue circle. So this is the algorithm. You have a classifier, number of samples, instance, and you sample around it. So for this I equals to some number, you can sample around and then you create this corpus of examples. So we'll go more in depth into this part. Oh, but first, so the classifier, you realize that there's no limitations. You can use any classifier. So this is model agnostic. So you sample around your inputs, and then this interpretable version X prime. We'll talk more about that later, but essentially this input is different from the actual model input. It's actually something that you can look at it and understand what it is. So this is the loss function that the line is trying to minimize. So first thing, we have a model. So any model will do. You take some vector and you output a real number. And so your input variables x is inside real d dimensions. And then you have an interpretable model, G. So for G, the input is actually binary. It's either 0 or 1s. And you can have an interpretable version that has fewer dimensions than whatever f takes in. So the dimensions is a d prime. Usually this is like, you try to make it as small as possible. You have a kernel, so the pi xz. So what pi xz does is that it allows you to measure how far this instance z is from x. So x is your original input, and then z is like some sample instance. And you have this omega g. So omega g measures the complexity of the interpretable model G. So G itself, there's no limitations. You can choose from a variety of models as well. And this omega G just allows you to weigh, like, is it better for you to have an interpretable model that's very complex but allows you, gives you a better explanation. Yeah. Okay, so if we look at the loss function again, there's this L, Fg, and pi x. So in the paper, the authors use this, which is a weighted square error. So essentially, you see that they have the Fz there. Fz is the actual model prediction. The Gz prime, that's the interpretable model prediction. And then you take the square error, and then you weigh it by how far z is from x, which is the pi xz. Yeah. And pi xz is the kernel, and the kernel definition is given there. So far, no questions, right? Crystal clear. Awesome. Okay, so moving on to example, text-based example. You have a sentence. For Christmas song, visit my channel, smiley face. So you want to find out the probability of it being a spam message, and you want to also find out like how strong you believe that it's a spam message. So an interpretable version could be something like this. You take some words and then you remove some words in the sentence, and then for each of the green ticks, you take the word that's associated with it, and then you calculate the probability that it's a spam message. So you can see down here the probability of spam is 0.17, and then you weigh it, which is 0.57, because it's not very close to the actual input. So this is the Zi, and you can do this multiple times. So you end up with a lot of different samples. So for each sample, you have the probability of spam, and you also have the weights, how close they are to the actual original input. Okay. And once you have this, you can put it inside your loss function, and you get an idea of which word itself, like which of the actual words here, contribute the most to the probability that it's a spam message. So over here, we can see that whenever the word channel is included, the probability that it's a spam message increases to 0.99 compared to the rest is 0.17. And the weights are also very high, so they are very close to the original input. So based on this, you can sort of guess that the word channel is the indicative word. It's what makes the model think that it's spam message. Okay, so this is for text-based classifiers, but this line doesn't just work for text. You can also make use of it in images. So for images, we don't look at pixels because there's too many pixels. So what the authors did is they used the concept of superpixels. Superpixels are just groups of pixels that have some similar characteristics. like color, intensity, etc. And the way that they select which superpixels to use is that they just gray it out. So if I want to select some portion of the image, I just make sure that that portion is in color, and then the rest of the image is gray. And so the authors also mentioned that this is not accurate if the color of the pixel itself is part of what you're trying to predict. So, for example, if you're trying to predict why this classifier thinks that an image is retro, it could be because of the image pixels being very sepia, like very brownish. So in this case, the line wouldn't work because it just grays out everything that's not selected. Okay. So this is an example of how it looks like when you use lime on an image. So original image on the left, the first one is trying to explain electric guitar. So this is the parts of the image where if you gray it out, it's going to not be electric guitar anymore. So moving on. We have seen how you can use lime to predict individual examples. So for each example, I can tell you what is the important bit of the input. But how do you do it for the whole model? So they have this thing called the submodular pick for explaining models. And what they do is they calculate the important features for each example. And based on all these important features, they greedily select a few up to some user-defined number, which helps cover all the important features in the whole set of examples. So over here, you can see that they actually have 5 documents and 5 features. So the F columns are the features. And the gray squares are the important features for that document. So over here, you see that they can select the second and the 5th document, which would give you F1, F2, F4, no, F2, F3, F4, F5, important the features. And yeah, so that's what they will select. If they only had 2 samples, they can only select 2 samples. Yeah, so they will select document 2, document 5, and that will explain 4 out of the 5 features. So if you had an extra sample capacity, you probably pick the first document, which would allow you to explain F1 as well. So we go on to the experiments. So the experiments are in 2 parts. First are simulated user experiments. So these are not real users. They just create a data set and then they try different methods to see how well each model explains, selects the good features to explain the model. So over here, it's sentiment classification. There's 2 data sets, the books data set and the DVD data set, both on Amazon, I think. So there's 2 baselines here. First one is Parson windows. I'm not very familiar with the Parson windows, but from what I researched, it seems like what they do is they calculate, they take each feature and then they calculate prediction probability function, and then they calculate the gradient of that function based on that one feature. So for the whole data set, you take one specific feature, you calculate the gradient of that probability prediction function, and then that's how you find like how important this function is, this feature is with respect to the classes in this data set. And you select the top K features based on this metric. The other one really is that they select features until the prediction changes. So for example, I have a set of words. I would randomly pick a word. Then if the prediction doesn't change, I will still continue picking words until I pick enough to change the prediction to something else. So that's how they select features in greedy. And the metric here is recall for golden set features. So the models here are both interpretable by themselves. They use sparse linear regression and decision tree. So you can find out which features are important in the full model. And they take the features that are usually activated for each class as the goal set features. It's a bit convoluted, but yeah, that's what they use. So so if you look at the recalls on the right side of the slide, Lime actually outperforms every baseline, so including Puzzle, Greedy, Random performs the worst. So we're still on simulated user experiments. So this is a trustworthiness. So for this one, what the authors did is that they took a random set of features from the examples, and you say that these features are untrustworthy. And then they say, like, we calculate the predictions if these untrustworthy features are removed, and see if the prediction changes. And if it doesn't change, that means that the classifier is trustworthy. So, on this experiment, the Lime still performs the best. And lastly, we have the classifier selection. So this one, instead of removing random features, they insert artificial noisy features. And these noisy features are randomly correlated with the classes. So they look at the classes and then they randomly insert some features. And then they try to see they train different models until the validation accuracy is within 0.1. So you can't tell which one is better based on the validation accuracy, but the test accuracy needs to differ by at least 5%. So this is trying to simulate a case where I have some random features that might affect my validation accuracy, but not my test accuracy. Test accuracy, there's still a difference. So based on this new classifiers, can I select the better classifier, better model based on the features that it shows to the user, like what it deems important. Okay. So a bit convoluted, but we go on to something a little less convoluted. So this is the actual human subject evaluations. So these are all people from Mechanical Turk. They take the religion data set from 20 news groups. They train it on either the original data or some clean data. So they remove words that shouldn't be in there. And then they test it on an external data set, external religion data set that they compile themselves. And they say that this submodular, the Lime outperforms Greedy. And the user feature selection, this is quite interesting. So there are multiple rounds of user testing. And at the end of each round, they ask the user to remove some words from the examples. So, like, let's say round 0, you have the full example. The user looks at the explanation, and then he selects a few words to remove. He says that these words are not useful for this example. And then they go on to the second round. They retrain the classifier based on the example with the removed words. And then they show it to another user, and the user says, like, oh, based on this new example, these other words are not important. And then they remove it, and then they send it again to the next, train the next model, then show it to another user. Yeah. So based on that, they actually perform, like, the words selected by the users on the line actually performs better than if you didn't clean. Like, if you just repeat the same experiment with the same data set, if you don't remove any words from the input. And last thing, image classification. So we talked about this briefly at the start, which is you have inputs that's very noisy. How do you gain some model insights based on the predictions? So this one, they classify wolf or husky, and then the wolf images all have white backgrounds. So they're trying to see if people can tell if it's a good classifier or not. So you can see that before they showed the explanations, 10 out of 27 people trusted the bad model, but after they showed the the explanations, 3 out of 27 believe that it's a good model. Yeah. Okay, so that's all I have. Any questions?